I'm going to start today with a quick review of the first exam. You should all be able to actually see it in your grade center now and click on it and see question by question where you got full marks or where you didn't, and also see the comments showing about the correct and incorrect answers so that you can hopefully understand where you went wrong, and that will help you in taking the makeup exam, which is also available now. The makeup exam is available up until just a bit before the second exam, because I want you to understand the material from this first section and have time to study for the second exam after you submit it. So you only have not too much time. You have about a little over 2 weeks, I think, if you want to take the makeup exam. But you get 3 shots at it. And I put lots and lots of time on it, really more time than you need. So you can take your time taking the makeup exam. So let me just take a look here. Here we are. So you'll notice, I think, a number of these questions are basically on the makeup exam again, but with different numbers. So they're slightly different, but they're the same kinds of questions. This first one, most of you got right. It was just a matter of counting the number of patients in each bar of this histogram. So what was this? The question was, how many patients stayed for 8 days or more? So there's 2 who stayed for 8 days. So 2 plus 4 plus 4 plus 2 plus 5 plus 2 plus 1 gives you the right answer, whatever that works out to be. It was 20. And then the second question was basically the same one, except just turning it into a probability by dividing it by the number of patients, which you were told here was 30. So those 2 are pretty quick. The third one was a conditional probability, a little bit trickier. What proportion of patients stayed in the center for fewer than 8 days? Actually, that's just 30. Well, 30 minus the answer for the first, I think it was 20. So it was like 20 out of 30 stayed for 8 days or more, 10 out of 30 for fewer than 8 days. And then dividing that through by 30 as well, or just going 1 minus your answer for the previous question. The fourth one, and feel free to interrupt me if you have a question about any of these. Let's see. Given that a patient has stayed in the center for 11 or more days, what's the probability that the patient stayed for 14 days? So this one is a conditional probability. You have to count up the number who stayed for 11 or more days. That's on your denominator. And the number who stayed for 14 is on the numerator. So this one would be just 1 patient divided by the number who stayed 11 or more days, which is 2 plus 5 is 7, plus 2 is 9, plus 1 is 10, so it's 10%. Or 0.1. Let's see. And in the cases where I asked you to go between 0 and 1, or asked you to give it as a percentage and you did the other, I just took a little bit off, like a half a point. Okay, this is where the troubles really started, calculating some probabilities. A lot of people got lost on these next couple of questions. Consider a diagnostic test for cancer that's 99% accurate on individuals with cancer. and 80. So that's the sensitivity. 80% accurate for individuals without cancer. That's the specificity. And then it's applied to a population with the prevalence of cancer is 0.01 or 1%. So the first question is, if the patient receives a positive test, what's the probability that the result is correct? What's this called? Sorry? PPV, very good. This is just a PPV question. There's no tricks about it. It's just a PPV question, except that it does make you sure that you can recognize the sensitivity and the specificity and the prevalence of it, so that you can plug those into your spreadsheet or your formulas. Now this one was where things really went wrong. If the individual receives a negative test, what is the probability that this result is incorrect, i.e. the tested patient has cancer? 1 minus the NPV, very good. This is one that actually made me worried that I've actually just confused you in this course. That I feel like probably before you took this course, probably you would have looked at some of the answers and said, no, that's impossible. It can't be this answer. Because, you look at these numbers, it's not a terrible test, right? Like, it's 99% sensitivity, 80% specificity. Like, it's not a, on the surface, it's not a horrible test. Maybe it's not perfect, but what kind of a test would give you, if you have a negative test, you have a 99% probability that it's incorrect. Like, you have a 99% probability of having cancer because you got a negative test. What kind of test is that? And a lot of people put that. So I really encourage, with a question like this, step back for a minute too. Like, don't get lost in the formulas and ask yourself, does this make sense? What's the sort of range of what you expect? You kind of expect, if you get a negative test, you shouldn't have too high a probability of having cancer. Certainly not 99%. Yeah.
I think I've fallen into that box that you were describing, where you were like, I'm going to paraphrase what you just said, where like the question seems easy, and then it led me just the way like I knew the answer, but it seemed almost too easy, and then I felt like I missed a step, so I changed the answer because I was like, it can't be this easy, right? So I'm looking at it, and then like I start reading, and then I start doing that same logic dance with myself in my head, right? And it's the first exam in the class. There's all these other aspects, right? And I, for one, studied heavy on the standard deviation and the bell curve and the charts. So now I'm stuck doing this, and I'm sitting here going, how the hell did I paint myself into this corner? Now I don't know what's left from right. So now I have to start all over again, and it gives me the same answer, which turns out to be right. But now I'm twice as more like nervous about the idea of whether or not I did this correctly, right? So all of that is kind of just to give you a glimpse into like what's, at least for me, like what's going on in my mind. I'm like, okay, fine, let's just go with this. And after a while, I'm just like, damn, I got this, but then I flipped it around and I got this, and I moved the decimal point, and I don't know what the hell I'm doing. So it kind of like started all over again. I took a wing and a prayer, and I was like, let's just keep it moving. Like, I would just exhaust every option until I move to the next question.
I think only like 3 people in the class got this one right.
And then we did the question 5. It was PPV.
Then, right. But then this one's not NPV.
So then you're like, wait a second. And like he said, you do it, you get it, but then you're like, no, I don't think this is correct. So you redo this.
And then you start thinking like, this wouldn't be MPV. I just gotta ask PPV. That doesn't make any sense. Why would there be 2 questions back to back like that? This is too easy.
Well, it's not NPV. It's 1 minus the NPV.
Right.
So in both cases, it's the probability that you have cancer, but what's the probability that you have cancer if you get a positive result and if you have a negative result? So, I mean, this this was a bit of a loop here because it's not NPV, and most of what you've done is NPV. But did it strike you as weird that you get a negative test and you have a 99? I mean, that was in a lot of cases higher than your probability if you got a positive test.
I mean, at this point, we're the Tuesday morning quarterback at this point. Like, I've seen it all. And I can analyze it. I can see what I did wrong. Like, it's great from now. We're like 7 days removed.
Okay, but you agree that in general, if you get a negative test, your probability of having the disease should be lower than if you get a positive test.
Yeah. Okay. Yeah, I understand the concept. Like, I get it, totally.
Yeah. Okay, good. So let's see, and then this one, if an individual receives a negative test, wait, no, that's the one we just talked about. The next one, oh yeah, this one was kind of all over the place too. Which of the following could provide a substantial improvement in the PPV of the above test? And I knew I was going to ask this question on the exam, so I know I really tried to like tell you the answer in the class where we were doing this. Remember when we had that one where the test had 100% sensitivity and it still had a bad PPV? Yeah. That was the case here. You can go up to 100% sensitivity. It's not going to have any effect on the PPV. This was formatted a little strange. Improving the sensitivity. So that one's out. Improving the sensitivity does not help. Improving the specificity without any change in the sensitivity. That helps a lot. That's your performance on the negative cases. I mean, if you get your specificity up to 100%, your PPV will be 100%. Because then you're never making a mistake on the negative cases, or the people without disease. Applying the test to a population with a higher prevalence of the disease, absolutely. And then this third one, increasing the threshold for a positive test, so sensitivity increases and specificity decreases. That's definitely wrong, right? Because what you need is better specificity. So that you're going to make it actually worse by doing that. Any questions about this one? Not many people got those two answers. So don't feel bad about asking me what's up. Does it make sense now on Tuesday afternoon? Yeah. Questions. Oh, right. This one was numbered wrong because I added more questions. In any given year, 1 in 3 Americans over the age of 65 will experience a fall. Oh, there was lots of trouble on this one, too. If you have 3 living grandparents over the age of 65, and assuming that the probability of a fall for each grandparent is independent, what is the probability that none of the 3 grandparents will experience a fall? So you have a few tools for doing this. Probably the easiest way is with your binomial distribution calculator. If you use that correctly, you put in, so the probability of a fall is 1/3, your number is 4, and your x is 0, and that'll give you the answer. You could also do it like with a calculator, saying that for each of them not to fall, the probability is 2/3, and for everyone it's 2/3 to the 4th power. So that would be the probability of none of them experience a fall. 2/3 to the 4th power should give you the same answer, as long as I'm not thinking something wrong right now. What is the probability that one or more grandparents will experience a fall? That's just 1 minus your answer in the previous one, or you could do it, probability with x equals 1, plus x equals 2, plus with x equals 3, plus with x equals 4. Get the same answer either way. So these ones, I mean, there was no trick with this question. This is just practice with calculating probabilities using the binomial distribution. I could do it right now in Excel just to see if I can get the right answer. So let's see. Binom.dist. So number S trials, so the number S is 0, the trials is 4, and the probability is 0.3333, like that. Oops. Oh, and cumulative, I'll say false.
You use 0 because you're calculating the odds that none of them will fall. You're doing the first question, right?
Right. Okay. Yep. So it's the probability of a fall. So we're going to call fall a success. Here is 1/3, and the probability of 0 successes in 4 trials. That's all there is to it. And then the answer to the other one, we could do 1 minus that. It gives about 0.8, but you could also do it. What's that? Yeah, you could also add them. So I could do it like this instead of, I'll put 0 here. Yeah. Copy, paste, and instead of 0, I'll use B5. Two, 3, 4. So I can do it for each of these. So what was the question asking for again? The probability that one or more. So actually the only is so yeah, it's either 1 minus this or it's sum of now C6 to C9. Same thing, about 0.8. So 80% chance that you have one grandparent who will experience a fall. Any questions? I don't know. Do you think I was being mean to you on these questions? Okay. No, I tried to be fair. Let's see. Okay, below are the data n equals 100 from a randomized trial designed to evaluate the effectiveness of a newly developed pain reliever designed to reduce pain, blah, 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 in it following joint replacement surgery. Okay, I know it can get kind of confusing just having to read about medical stuff. I don't know about joint replacement surgery, but let's get to the question. So here is one of these 2x2 tables with the new pain reliever and the standard pain reliever, clinically meaningful reduction in pain and no clinically meaningful reduction in pain. What is the probability of experiencing clinically meaningful reduction in pain given that the patient received the new pain reliever? So here's the clinically meaningful reduction in pain. And given that they received the new pain reliever, so that's 50 people, 33 divided by 50, 66.66. I could be putting in my answers here and see how I'm doing. But if any of you have the exam up, you can tell me if I'm getting something wrong. What is the probability that a patient in this trial received the new pain reliever given that they experienced a clinically meaningful reduction in pain? So the other way, given that they experienced a clinically meaningful reduction in pain, that's 66 people. Probability that they received the new pain reliever is 33 out of 60. Okay, and then this, the one that I thought was going to be like horrible for you. You guys did fine on this. Like most people got these. So there was a bit of trouble on this. I ended up being very permissive on grade and tumor stage. I was like, okay, you're not cancer researchers. You don't necessarily know that like there are multiple grades and higher grade is worse than lower grade and higher stage is worse than lower stage. So these are our ordinal variables. Plus, I think they actually were coded incorrectly and they're coded as nominal in SPSS. So if you said nominal or ordinal, you got full points on these two, but they are ordinal variables. Age, that's quantitative. Debulking, that's nominal because it only has 2 levels. You only have 2 levels, it's a nominal variable. You can't have an ordinal variable where you only have 2 values. Like optimal, suboptimal can't be ordinal. 1, 2 can't be ordinal. BRCA1, BRCA2, and TP53, these were all quantitative. And I didn't even put in like discrete in here because so that you would, I didn't want to mix anyone up about age or make, maybe you could call that quantitative or discrete, but discrete's not there. These, yeah, most people got these right. I mean, if you clicked on that SPV file, there were your descriptives. So I actually made one of these the scaling variable. I scaled this up by about 5 points to get you to the median that I wanted. And I used one of these. I think the minimum and the maximum everybody got right. I don't know. I guess the quartiles, there was a problem with some people. Maybe if you weren't using SPSS and didn't know how to calculate the quartiles in Excel. Which has a bimodal distribution. This one, if you were able to create a histogram in SPSS, this was an easy question because this one is completely bimodal. It's like the most perfect bimodal distribution you'll ever see. Which one has the most right skew? That's the one that skews way to the right. These ones, if you were able to make the histogram, they were pretty easy. Only the way I think you got it, didn't get these is if you're having trouble making the histogram. Now some probabilities. These caused some more difficulties again. So this one is used, now we're getting into our normal distribution questions. Mean of 55, standard deviation of 6. The probability that a randomly chosen 10-year-old is shorter than 48 inches. You can do this by converting this to a z-score. That's minus 7/6 is your z-score. You can take, that's 1.166 or something. Look that up in your z-table or in Excel. What's the probability that a random chosen 10-year between 60 and 65? Here you just have to do it 2 times for those 2 z-scores and take the difference. What's the height cutoff for very tall? Sounds confusing, but this is just asking for that right tail distribution. So this is at what value of z is there 90% of the probability below there. Once you get that value of z, you can convert that into a value in inches. Okay, and then again, what percentage of 10-year-olds are below 54 inches? Just yet another Z-score question. Lots of these. And another one, according to BRFSS, 58% of Americans adhere to a sedentary lifestyle. He took a sample of 10 individuals and find that 8 of them do not exercise regularly. What is the probability of finding 8 or more individuals who are sedentary? So this is actually a binomial distribution question. So the probability is 0.58. I could try to do this. Let's see if I can do it on the spot. I kind of love but kind of hate trying to do questions on the spot. It's a lot of pressure, but it feels good when you are able to do it. So let's see. So I'm going to do equals binom dist. So the number of successes here, 8 or more individuals who are sedentary. So I'm going to use 7 for the number of successes out of 10. The probability of 0.58 and cumulative true. So that's going to give me the probability for 7 or less. And then 1 minus P5 should be the probability of finding 8 or more individuals who are sedentary. Did I get it right? Yeah, okay. I'm not cheating, I don't have the answers here. Now this one actually, you could do a calculation here, but you shouldn't have to do a calculation. You could just go ahead and do it again and see whether it's more or less, but you should be able to answer this intuitively, okay? Because with that probability 58%, just tell me, like off the top of your head, would you be surprised if say you pick one person and they're sedentary? Does that seem like something really unexpected? No. 2 people and they're both sedentary? A little more unexpected, you know, but still not too unexpected. How about if you pick 20 people and they're all sedentary? That's really unlikely. It's not going to happen. So, you know, the same, like, you know, so this is above the average, above 58%, it's 80%. The larger the sample that is, the less likely that's going to be. You know, and if you looked at 1 million people, you're not going to find that 800,000 of them are sedentary because this probability is 58%. You know, so the larger that number, the more close it should be to the population average percent of sedentary people. So it's got to be less, right? You don't even have to do a calculation. And then this one was I just put on for fun. I actually saw this in an XKCD cartoon just the week before the exam, and I thought I would put it on. Which of the following contains approximately 50% of the probability of a normally distributed variable? This one you should really be getting right. How many times have you looked at sketches or figures like this in this class? Just throw out a number. How many times? It doesn't have to be right. Approximately. What's that?
I said 50%. The question asked which was 50%.
50% of the probability. So all these times that we like calculated probability, and I showed, you know, different areas of probability. How many of them look like this?
I wasn't sure that graph, it includes actually the bar graph, right? So if we calculate it this way, this can be 50%.
This can be 50%?
Like if we do a bar graph.
Bar graph.
X-axis and y-axis, because this is basically a bar graph.
So I've drawn on here, this is height on the x-axis, and this is probability. So, you know, this is a normal curve. This isn't anything.
Yeah,
The joke in the cartoon was that this made statisticians' heads blow up. The drawing this shading an area like this on a probability curve, because we don't know what that is. This is how we draw probabilities. Any other questions before we go on to the lecture? All right. So the makeup exam, I just submitted an exam with no answers. Things are looking a little funny. I forget the exact date, but you have the announcements for when the makeup exam is due. What's up? And again, the rule is you can take it up to 3 times. It'll be your last attempt that counts. You're not going to get to see the answers after first ones, but you'll get to see which ones you got wrong, so you can work on them and then do it again with the and hopefully correct the ones that you got wrong. And then I'll take the average between this exam and your makeup exam. Okay. We're moving on to, this is going to be a fairly short and fairly conceptual class today. And I'm going to introduce to you the difference between a population and a sample. I'm going to try to explain to you what a sample is. And with that, talk about sampling distributions. And if I can only get you to understand one thing from this class, it's going to be what a sampling distribution is, because it's really fundamental and it's really little understood among public health professionals and the general public. So I'm really going to try to get you to accept and understand what a sampling distribution is. It's something really cool. You're going to like it. And then I'll talk just about some different experimental designs. You're going to hear way more about these in FE than in biostat, so I'm not going to go into them too much. Experimental versus observational studies and prospective versus retrospective. So at the basic level, the population, as we've talked about already, is everyone that is of interest and who can be part of a study. So I think we talked about the target population. That's the population that you would like to study, and your study population, which is whatever subset of that you actually have some non-zero probability of including in your study. And that population could be, could be the whole world, like that example we did. It could be just the state of Massachusetts. It could be just adults. But it just has to be defined and a group where we can define what the population is, and we can list them as records so that we can sample from them. And a sample of them, these are small subsets selected with a size that will be practical for us to study and be just big enough to be able to infer something about the population. When we calculate things from samples, like the sample mean, you remember we use the Roman letters like X. Sample mean is X bar. And things about the entire population, we use Greek letters for those like mu, and we call them parameters. So things about the sample, those are statistics, and things about the population, those are parameters. And a lot of what we do in statistics is about taking something that we measure on a sample and making inference from that about the whole population. So study units are sampling units. Those are the individual elements of interest, like a person. The target population is that ideal population we would like to describe, let's say like the state of Massachusetts here. The study population is the ones from which we actually sample. So if we're using like, you know, a random phone dialer, it's only going to be people who have phones. The sampling frame is this list of all units in the population from which we use for sampling. So if it's going to be we send people door to door, then we're going to need a list of all addresses so that we can randomly select from them and send people to knock on those doors. If it's going to be a phone survey, we need an enumeration of all of the phone numbers so that we can randomly select from them. There are a few common sampling strategies. The simplest one and a commonly used one is the simple random sample. This is the simplest kind of sample. All it is we randomly select people from the population. That is it. So if there are, I don't know, what is this, 20 people here, and we want a sample of size 10, we just randomly, we throw their numbers into a bin and do it like the lottery, or we use a computer, but we just equal probability for everyone. We just pick out our desired sample size. Systematic sampling. I have the wrong picture here for some reason. Systematic sampling would be where we selected some number to start on. We have our sampling frame, our enumerated list, and then we just go every nth record to select for our sample. So this could be a practical thing. Say if we're doing house addresses, instead of randomly selecting house addresses, we take like every 10th house if they're ordered in some systematic way, and we go every, say, 10th house. That would be a systematic sampling. And you can often treat that as a simple random sample, depending on how the records are ordered. If the order of the records is randomized, then it's the same as a simple random sample. If it's somehow geographic, then it's not the same, but it actually guarantees you, and I'll give you an example of this, but better like even distribution of records in your sample across the population. Now, stratified sampling is slightly more complicated to do, but it's actually a very good strategy, and a lot of a lot of studies should use stratified sampling. And the only difference between a simple random sample and a stratified sample is that you first separate your population into these so-called strata. So we have here, you know, our blue, our black male restroom figures, and our female restroom figures with a pink outline, I guess. Oh, it looks different up there, or red. Anyways, you pick some feature that you expect to have an impact on whatever outcome you're studying, whatever you're studying, and you stratify based on that. And then you take simple random samples from each stratum with pre-specified proportions. So you might then decide to take 30% from each stratum or an equal number from each stratum. And this has the advantage that anything you then calculate from your sample, it's going to have less random sampling variability than a simple random sample, because your proportions of these strata, something that matters, are fixed. So this is a good strategy, and something that if you're ever involved with designing a study, it's something you should probably review a little bit more than this and consider using it. Yes?
When you use this sampling form, does it still have to be the same number of people in each group?
No. No, your strata, they could be 10% in one, 90% in the other. It doesn't have to be the same number in each group.
They just have to share like a common factor in that group.
Yeah, it's a way of controlling random variability due to something where you know there's like systematic differences between them. Like, you know, if you wanted a measure of like, you know, the height of the population, and you're going to have a small sample, you know that like males and females have different average heights, you would get a more accurate measure if you took a stratified sample of equal numbers of males and females than if you just took a random, you know, a random sample. Suppose you have a small sample, 8 people. If you just did a simple random sample, you could end up with, you know, 7 males, 1 female, and you're not going to get, you know, you're definitely then not going to get a good estimate of like average heights of females then. And your overall estimate is going to have more variability. You'll have a good estimate for males, not for females, and not overall. You're going to do better by stratifying on this thing that you know affects what you're measuring. And it's also a way to, like in the National Haynes study, Health and Nutrition Examination, and the other surveillance surveys, they use stratified sampling also as a way of getting better representation of minority populations. Because if you just do a simple random sample, you end up with like your majority groups, you have a larger sample size than you need, and your minority groups don't have enough to do anything useful with. So they'll actually, you know, oversample the smallest groups so that they'll still be able to estimate things based on them. Like if you have you like in a state where American Indians are a minority population, but you want to surveil the health of everyone in the population using some average measures, like, you know, the average proportion of sedentary behavior. If you have a limited sample, you had better oversample those minority groups if you want to have any kind of a reliable measurement for them. And you don't need, one of the interesting things that I'll talk about later in here is that with samples, no matter how large your population is, you only need to make your sample so big. if it's a proper random sample, like n equals 30 is a large sample, n equals a couple hundred is getting to be quite a large sample. You know, there's really diminishing returns beyond certain sample sizes. So that's a place where stratification can be really useful, so that you're not wasting your resources sort of over measuring some populations. Cluster sampling is something that is kind of common in public health studies, and this is where you have different units of sampling. So if you're doing like an intervention in schools where it's not practical to to provide this intervention only to individuals in a school, it has to go to the whole school or not, then you're going to do something like a cluster sampling where you pick entire schools to do some new, I don't know, public health messaging thing. Even though the individual is like the level where you're observing the result of that is individual students. So it's where you have different levels of grouping. You have individuals, you have some other bigger group by which individuals are grouped, and you do random sampling potentially at each of those levels. So first you randomly select schools to apply this intervention, and then you randomly select students within that school to measure the effectiveness of it. And that, what I just described, is called a cluster randomized trial. It can also be cluster sampling in observational studies. Like you're going knocking door to door, maybe it's not practical to try to go around all of New York City, but maybe it's practical to pick like some zones and, you know, randomly select zones around the city and focus your efforts in those zones. You don't have to go to every house within a zone, but by doing that, you don't have to cover the entire area of all 5 boroughs. And then there are non-probability samples, which are often also called convenience samples. These are things like people who volunteer for a study, patients at a cancer clinic, people who answer an online study. All of these, we don't know the probability of selection. And it's not even clear who the population is that you're selecting from there. The key thing is that we do not know the probability of selection, and therefore it's prone to selection bias. And you know, you only do this study when it is necessary. Sometimes there's no alternative, but it means that things like p-values that you calculate, there's a good chance that those p-values are wrong, because you can't necessarily make accurate inference about the population when you don't know how representative your sample is of that population. You just have to assume it's representative. So here's an example in on a map. If you were to apply all of these to sampling sites on a map where this area has been divided into equal squares, a simple random sampling would look something like this, just spots placed all over the map randomly. A systematic sample would look like this, placed out on a grid. So you can see that, you know, you're not going to get the same kind of like little groups of close together sites, and also no big deserts where there was no sampling done. Stratified random sample, in this example, they're saying, okay, we want a certain number north of the river and a certain number south of the river, and that way we're guaranteed to have a certain number on each side of the river, even though that there can still be some variability on each side. But in general, there aren't going to be as big gaps in the stratified sample as there are in the simple random sample. And non-probability sampling would just be maybe we just follow areas of interest. Let's follow this ridge or whatever it is and take a look around this area. So in order for something to be an experimental study, there has to be an intervention. You have to be actually changing something, not just observing your units of observation. Okay? You have to intervene and you have to randomize that intervention. Now I'm going to ask some kind of question about this, and I'll make some very scientific sounding study and say, is this observational or an experimental study? And you might be tempted to say this is experimental because there's a lab involved, there's lots of science, but unless there's an intervention, it's not experimental. So it doesn't matter that you take your samples to a lab, you apply lots of technology to those samples, that doesn't matter. What matters is that there's intervention. So for example, if we're talking about cancer patients, if we randomly assign patients to a standard of care or a different treatment, then that's a randomized controlled trial. If everyone receives the same treatment and we observe differences based on, what their body mass index was before treatment, that's observational. So even potentially the same population, still talking about cancer treatment, it might be observational or it might be experimental depending on whether you're using a randomized intervention. And observational means there's no intervention, just like it implies. You're just observing. So some examples, a cross-sectional study is a random sample of the population at a snapshot in time, like New York City Health and Nutrition Examination Study, Behavioral Risk Factor Surveillance System, and the National Health and Nutrition Examination Study. These are where they have the population of the US from a census, and they randomly select people on 1 year and go and try to give questionnaires and health exams to those people at a snapshot in time. Retrospective is where the subjects are recruited based on health status. So you go and try to identify people who have had cancer in the past, and then ask them, did you smoke? Did you drink? And try to determine something about whether these things cause cancer based on looking back in time. And prospective is where you find a cohort, such as a bunch of nurses, get them to sign up for your study, and then follow them in the future through time, such as the Nurses' Health Study. And it's important to remember that observational studies like this cannot prove causality. They can show correlation, but they cannot prove causality. Doesn't mean that these correlations are not causal, but you can't prove it. So, there are cases, success stories where observational studies over time have built up good evidence of causality, but it takes a lot of sort of time in different populations and very careful ongoing replication and very thoughtful consideration for the possibilities of unrelated confounders, mediators, colliders, things that you might hear about in your fundamentals of epi course that can make unrelated things look causal. I think Tony has some good examples of spurious correlations. So in an example, does smoking cause lung cancer? An experimental approach would be to find a bunch of people who've never smoked, randomly assign them to smoking and non-smoking groups, follow them for some years to see who develops more lung cancer. Now, there's an intervention there because you're either telling people to smoke or to continue not smoking. That's obviously something that you cannot ethically do, but that would be sort of the most direct experimental approach to answering this question of does smoking cause lung cancer. It's never been done. There's another approach, though, that could be done ethically, which would be to randomly assign smokers to no intervention or to a cessation program that helps improve the rate of cessation and follow them for years to see who develops more lung cancer. Now, this is experimental because those smokers have been randomly assigned to no intervention or to a cessation program. What if you just found smokers who had entered a cessation program and then found other people who never entered a cessation program and followed them both to see which groups. So say we go to a stop smoking clinic, recruit a bunch of volunteers for the study because they're in the cessation program, and then for our control group, we go find another group of smokers who are not interested in cessation. Is that an experimental study, an RCT? No, that's observational because we're not intervening. We're not telling them go into the cessation program or don't. So in that case, it's possible that there are other differences between the cessation and non-cessation group. You know, just for a starter, they could be different in age. Maybe as you get older and you've been smoking for longer, maybe you're less interested in cessation programs as younger smokers. So there can be systematic differences between those groups. Observational approaches, the cross-sectional approach would be to survey a sample of the population, ask whether they've been diagnosed with lung cancer and how much they have smoked. So there you're just doing it this snapshot in time. Retrospective, recruit 50 cases with lung cancer and 50 controls who do not have lung cancer and see which group smokes more. And prospective would be to recruit your bunch of nurses or something, follow them over the years, ask them every year how much they smoke and see which group develops lung cancer more frequently. So these are obviously easier studies to do. Cross-sectional, you can do it in a single year. Retrospective, you could also do that in a single year. Prospective is harder. You have to follow them for a while. But all of them, it's just a matter of like collecting information. You don't have to provide a cessation program. You don't have to try to really encourage one group to go into smoking cessation. You don't have to get anyone to change their behavior. All right, now I promised that if you came out of this class with one thing, I hope that it was going to be knowing what a sampling distribution is. So I've saved it for last to make the most impression on you. So here's an example. These are 16,000 runners in a data set where we have all of their running times of every individual. So let's consider everyone in this run to be, well, I'll just ask you, is this a sample or a population? What's that? A sample? Why do you say a sample?
not the entire population.
No, but it's everyone who ran this race. I mean, we didn't sort of randomly select people from the population to run this race. So I'm going to say that, plus it's a lot of people, that this 17,000 people, these 17,000 runners, these are the population of people who ran this race. I'm going to consider that a population. And then this distribution of finishing times is a population distribution. It's the distribution of completion times for the entire population of runners who ran this DC Cherry Blossom Run. So if you calculate the mean, is that mu or x bar? It's mu. It's mu because it's of the population. It's not x bar. I mean, it's not going to make any difference. The calculation will, whether you're dividing by n minus, well, no, sorry, for the mean, it's the same anyways. But this is the population mean, if this is everyone in our population. Okay, now, if I randomly sample 100 runners, what is that then? That's a sample. That's definitely a sample. I randomly sampled 100 of them and plotted their completion times. And how would you characterize this distribution of 100 running times? Yeah, this is a sample. But this distribution looks pretty similar to the population distribution, right? It's a random sample. The middle is about the same. It's just under 100 minutes. You know, the variability, it's about the same. Most of them between 40 and 140. By and large, it looks similar. So this is a sample, but if you look at the distribution of times within the sample, it looks like the population. So you could call this an approximation of the population distribution, but estimated from a sample. So what is a sampling distribution? It is the distribution of a statistic for many samples taken from one population. So if I took that sample that I showed you on the last page of 100 runners, I calculated some sample statistic like x bar, the mean, and then I repeated over and over. And every time I took another sample of 100, I calculated x bar, I get a whole bunch of numbers. That bunch of numbers is a sampling distribution. And that is fundamentally different from the population distribution. And that's what I want you to get out of this. And you'll see it's really different. Unlike here, where they look kind of the same, actually the sampling distributions look really different. If the population distribution looks something like this, a big wide bell curve, the distribution of, if these are sample means, it'll have the same center, but it's going to be a lot skinnier, less variable. And this kind of makes sense, right? So here, this is cholesterol levels. You can imagine that, you know, if you look at individuals, there could be a pretty huge range of cholesterol levels from people who have very low cholesterol to people with very high cholesterol. You know, there's quite a variability. But if I take a sample of 10 people and average all of their cholesterol levels, it's not going to be as variable as individuals. If I take a random sample of 100 individuals, their average cholesterol is going to be even less variable, right? The average properties of groups is not as variable as individuals. Just like, you know, individuals have individuality, groups have group characteristics that are not as variable as individuals. And this is a really fundamental property of samples, that the average property of samples is less variable than individuals from the populations that they came from. So in that example, the median for the whole population was 33. For 100 runners, it was still 33. The mean was 36 for the population. For the 100 runners, it was 35, pretty close. Standard deviation overall is 10. Standard deviation for 100 runners was 9. All pretty similar, just a little bit of random variability here in the sample. So I've already given you the answer. Now I'm going to ask you the question. Is this histogram of the sample an approximation of the population distribution or the sampling distribution? Put your hand up if you think it's an approximation of the sampling distribution. How about if you think it's an approximation of the population distribution? Whatever, what's good stating?
I think it's the approximation.
Hmm? Thank you. I mean, look, these numbers are all about the same. This distribution is an approximation of the population distribution. These numbers are all pretty close to the same. You know, and the middle is about the same. The spread is kind of similar. And what did I tell you that a sampling distribution is?
Added. Yeah, so
you have to take many samples. Many samples. This is just one sample. So you have to take many samples and, let's say, calculate the average of every sample to get your sampling distribution. This is just one sample, so that is not an approximation of the sampling distribution. The hard thing about a sampling distribution is that you never observe it in real life. You only ever get to work with one sample. You'll get to see individuals in one sample that are going to have a similar distribution as in the population. This sampling distribution is kind of a theoretical thing. It's fundamental to statistics, to all of statistics, but you never actually see it unless we do a simulation, like where we repeatedly take samples of 100. But in real life, when you study a data set, you're going to have one sample. So this mean of 35 is just 1 point on a sampling distribution. And if we were to take more and more samples of 100, that would be a sampling distribution. Does that make sense? This is something, yeah, I hope you can take this home with you. You don't need to know math for this to understand what the difference is between a population distribution and a sampling distribution. Now the last thing I'm going to do today is tell you about the central limit theorem, which is important, like it sounds, because what it does is it relates the sampling distribution of the means, so means of a bunch of samples, to the population distribution. So like I said, you never get to directly observe the sampling distribution, but using this central limit theorem, in certain situations, this allows you to estimate that sampling distribution. And the three components of it are, one, that the mean of the population and the mean of the sampling distribution are identical. Those two distributions have the same mean. So the average cholesterol levels in the population are the same as the average cholesterol levels in a sample over, if you take those samples over and over. It makes sense, right? Number 2, the standard deviation of the population, sigma, is related to the standard deviation of the distribution of sample means by this formula. Sigma over the square root of n, where n is the sample size. And this standard deviation of the sample means has a special name. It's called the standard error. So remember again, this standard error is something you're never going to observe directly because you will just have one sample. To observe it directly, you would have to, say, get 100 samples, calculate the mean every time, and then the standard deviation of all those means. That's not going to happen, but you can do this. And then finally, for large enough sample size, the shape of the sampling distribution of means becomes normal. And this is pretty incredible because it actually does not matter what the population distribution was. So even if for a population distribution that is uniform, the sampling distribution for samples of size n equals 4 starts looking normal. And the larger the sample size, both the smaller the standard error will get, and the more guaranteed you are that it is normal. So that's pretty incredible that no matter what the distribution of cholesterol levels is, or income levels, or any other, TP53 levels, which was bimodal, right? If you take samples of large enough size, let's say of 30 patients, that distribution of sample means will be normal. So it's a pretty amazing result. And the standard deviation of that normal distribution, the standard error, will get smaller and smaller the larger n gets. Let me see. How am I doing here? Oh, I think that came across clearly enough. I'm going to skip ahead a little bit. Just say that n equals 30 is considered a pretty large sample size. The central limit theorem is fairly strong for n greater than 30. It does depend, like a distribution with extreme skew will have sampling distributions that are less normal. And also out in the tails of the sampling distribution is where deviations from normality will first start to be noticed. For a proportion, so with a proportion, we tend to call one of the values like optimal, suboptimal debulking. We code one of them as 0, the other one as 1. The proportion is just the sample mean of those 0s and 1s. And then for a sample, that mean would be the proportion of a sample. And it turns out also to be normally distributed, just with a slightly different formula of the standard error. So if you drew, let's say your probability of having suboptimal debulking of an ovarian cancer surgery is 40%, and our sample size is n equal to 30, you would just plug 0.4 in here, plug 30, and that would tell you. So you know that the mean is at 0.4, and the standard deviation or the standard error would be given by this. You'll get more chance to practice this in the lab. I don't want to cloud you up too much now with formulas after having explained the most important thing to you. So we're going to use this both for inference once you know that sampling distribution, you'll be able to estimate, like, you'll be able to calculate the probability of something being the true mean, because you'll have estimated what the sampling distribution is, and you'll also be able to calculate confidence intervals. I'm not going to get into those today. We'll get into those in more detail next class, but these are important applications of the central limit theorem. And they form the basis for the t-test, analysis of variance, confidence intervals, many of the most important things that you get from this class. And with that, I'm not too far behind schedule. I'm gonna call it quits for lecture. You can take, let's say 10 minutes, and we'll start up again at 6:30.